Cool. So I guess we can start. Welcome everyone again. Because this recording has started, I'll repeat it. This is my 50% seminar for my PhD. I've been here 2.5 years now, and hopefully you will see what I've been doing. And yeah, I'll begin. And this talk is basically Gustav and Jonas for poking me like, come on, do something. So the contents of this presentation, I will summarize, will be a lot of memes. And there will be the probability salad I've been talking about. I will talk about a little bit about neural HMM TTS, which I also presented last year. And then we did some things more on top of it. One we call OverFlow. Then I will sprinkle some evaluation, which I did with Ambika. And at the end, I will talk about Diff-TTSG, which is diffusion model-based synthesis, which we submitted recently. And there will be very little information, one page about that. I also help people with courses and try to supervise some students, even though I fail at doing so. Right, so I will quickly summarize what we did last year. I think from the time I presented last year, I will just cover those aspects of it, some other things that I found with neural HMM TTS. So what exactly was neural HMM TTS? It was we found Gustav found problems with attention-based TTS systems that they were slow to train, and they could break down into gibberish and start producing random noises, and they required more data to work at all. So this was our patch to it. So we were looking for a way which we somehow can enforce monotonicity. And there have been some other concurrent works that were doing it. And we proposed a new method, which was fully probabilistic. It could maximize exact sequence likelihood, and no external alignment tools were needed for that. So we talked about neural HMM TTS, which we presented at ICASSP. It had a learned front end, which was learned text processing. It had we used Mel spectrogram as audio representation. It was an autoregressive system, so it generated the smoother utterances, smoother melts, which I will talk about a little bit. And because of the HMM's property to be left to right, it was left to right monotonic in nature. And there was also a state transition probability, which looked more natural how to end the sentence, which I will again talk about a little bit about. And there was no LSTM in output. I don't think it really matters. It's just it's a residue from my ICASSP slide. But one important thing was there was no postnet in this. Other systems that we were comparing against had a very strong causal postnet, which so one of the things was why it is just one spice level, because it was very good, but it could not be state of the art. Right, it had the problems because it had half the number of parameters. We could not add something postnet to post-process whatever the output was here in some sense. So that's why it was just mild. My probability salad, as an Indian, I needed more spices to it. Some good things about it. As I said, that we had autoregression. The benefit of autoregression was that the things were no longer stepwise. The synthesis was smoother. So this converted into this, which so this is without autoregression and this is with autoregression. And people who work with Mel or have seen Mels before can say that this will sound much better than this one, even if you use like Griffin-Lim or something. Some other cool things, it solved the problem of awful state durations, in some sense that these transition probability without autoregression became, wait for it, look at my great animation, these transition probabilities with autoregression. So sort of each state learned to have a little bit of memory. In some sense, I'm over exaggerating it, but it had a little bit of memory, how long it has come in its duration, and should it switch to a next sound or not. So in a very low level understanding. And the state transition probability, it was a more natural way of deciding when to stop. So back then, state of the art was Tacotron 2, which used to synthesize like this. Should I stop? Should I stop? Should I stop? Should I stop? Which is not I don't plan my speech like this. Otherwise, I will be not speaking like this. So neural HMM, it goes like left to right. That's how I also decide my speech. That, oh, maybe I have finished my sentence. Maybe I should shut up now. So cool. And we presented neural HMM at ICASSP 2022. Oh, wait, sorry, wrong photo. Yeah, that was me presenting it. So then we moved on. Now we had a cool system that works fast with small data set and learns fast. So what about a little bit of messy data, like spontaneous data, which is more varied? And as we can see that it has more pitch variation. It has weird speech rate differences in the speech, which generally how people speak, but the recorded speech is very much, it's less varied. It's more monotonic in nature than the spontaneous speech. And then Harm was like, I'm on it. Harm went in there and he made the Prosody-controllable spontaneous TTS with neural HMMs. So we extracted the F0 standard deviation, F0 and speech rate from the spontaneous dataset, conditioned the network to model it explicitly, and now we could synthesize with control. Harm would have told you more about it, but I will quickly just play two examples.
It's a lot of people just like talking.
So this is where we forced the audio to be low, like has a low F0. I wonder if I've shared the audio.
Yeah, so we should ask maybe if they could hear it, then they could do a thumbs up or something.
Could you hear the audio that was synthesized? Oh, okay. My sister says they should thumbs up. Okay, cool. Then
The part it's just a lot of people just like talking, and it is difficult to connect.
so this is when we forcefully synthesized with high F0, and the data set was very weird, as you can hear. But we had control, so people at ICASSP 2023 liked it, and but it was not spicy enough, you know.
Can I ask you just a question? Like,
Yes.
How did you calculate that zero, like in conditioning? Did you use some million values or some?
Right. So Eva did it, and she split the audio into like different breadth groups, and then ran like a F0 extractor toolkit, so sort of wavelet prosody toolkit, and we got an F0 for each breadth, and then we conditioned it, and because we
On the mean of that.
yeah, and because we then standardize it, so we could do like +1 or -1 to essentially go up one standard deviation or less one standard deviation,
Right,
while synthesizing.
but you would kind of get a voice that is like high pitched all the time. It's not like how varied, but becomes that in the sentence.
So we had this as an external feature. So we added one more like F0 standard deviation.
Oh, okay.
So you have like a standard deviation flag. So if you will say that be high pitch, but also varied. So it will try to be as high pitch as it can while having a little bit more variety or variance into the pitch value. Cool. So yeah, so it was not spicy enough because speech acoustics are not Gaussian. We were using this mu and sigma here, which are Gaussian parameters. So we needed a post-net. And then also Gustav was like, I need more stronger probabilistic models. So so enter the normalizing flows, right? So what normalizing flows, they are a series of invertible transformations that can transform data distribution to more complex distribution. And it helps, it's very useful to do efficient probabilistic inference, and they can compute exact sequence likelihood. And you can also like sample from it, which I will show later, which is pretty cool. So, oh yeah, sound alert. This is a true story of what happened.
Don't let your dreams be dreams. Yesterday, you said tomorrow. So just do it. Make your dreams come true. Just do it.
So this is what happened. And we did this. We paid OverFlow, which is we put flows on top of these neural transducers for better text-to-speech. So neural HMM, instead of now autoregressively sampling the mel spectrogram, now they sample some sort of latent vector, which is latent basically means like it's not seen. And then we feed this latent vector into invertible normalizing flow-based postnet. And now suddenly we could model highly non-complex, highly complex non-Gaussian distribution of these speech acoustics. And not just that, and it became medium spicy. As an Indian, I like it. Right. And we submitted to InterSpeech 2023. People at ICASSP didn't like it, but that's another story. So it is now probabilistic in nature, and we can sample different realization at different temperature, and they all sound pretty good, I would say. It had high naturalness. We beat the previous state of the art this time. Woohoo, Takatron. And yeah, so we had the best mean opinion score. Yeah, most here refers to mean opinion score. It was like you crowdsource a lot of participants and they rate your audio, how good or bad is it. And it's also very fast and accurate learning. So if you see this log plot of the validation, so what we did, we synthesized all the validation utterances at like different time steps while with different checkpoints while training, and then ran like a whispered ASR. And with those texts, we calculated word error rate. And it turns out like to get like under 5% word error rate, our model only needed 2.5 hours of training, while the old state of the art needed 54 hours, and other parallel models. So they are not autoregressive. So they have this advantage of faster training and faster inference. But even they were like, we were comparable to that. So while maintaining the quality much better than what they could have even at the end of our training time, which was 100,000 iterations. Cool. So audio sample times. I've talked a lot about how cool it is. Now I will make you hear it.
It is now possible for presidents to travel the length and breadth of a land far larger than the United States.
And good thing is, like, generally people post stuff about which is cherry picked. The good thing is I didn't really need to cherry pick. So all the syntheses were pretty consistent. They were very good. And I feel this is something that in speech synthesis, people do like a little bit cheating there. But LJ speech is a very horrible data set if you will listen to it. So we also tried it with other data set.
Can you ask for help in the form of a question? Can you ask for help in the form of a question?
So there are two different realizations, two different samples, but they are more or less, they make sense in a way person cannot utter this sentence, right? And we also tried fine-tuning to different accents and different voices. Also, this is what happens with me every time I create a new TTS system. It's every time the first sentence that I test is like, the birch canoe slid on the smooth planks. And this is me like, oh. So, we had 7 hours of data set from an Indian accent, which I got from like IIT Madras, there's the university. And
The birch canoe slid on the smooth planks.
it sounds like an Indian guy, to me at least. And there was this Arabic data set, which was 1.2 hours of Arabic data set.
The birch canoe slid on the smooth planks.
Mandarin,
Birch canoe slid on the smooth planks.
British. The data set is less than an hour. So,
The birch canoe slid on the smooth planks.
and also there was a native Nigerian speaker, and the data set was like,
One birch canoe slid on the smooth planks.
so it could, with the quite a lot data set, could fine tune to very cool accents, which I think was very useful and fun for me to play around with. So even though this was not part of any evaluation, I did put some samples on the web page for people who actually work with these low resource settings can use this. But often in evaluation, we get stuck in the mosh pit. Wait, I will try to. Gustav, can you kick at this point? Yeah. So it will remove. Yeah.
I'll do something. You can keep going.
Yeah. So this was me. Every time I'm never able to reproduce the results, baseline results reported by papers. And they claim to be defeating natural human speech with worse quality on the sample web page. On a scale from 1 to 5, they'll put like 4.99999 MOS. I mean, okay, these numbers are over exaggerated, but my feelings are not. Right. So yeah, it's been 2 years. We've been trying to reproduce several baselines, not to name some systems, but people who have worked with me know what I'm talking about. And we've never been able to. Yeah. So one day Ambika said, these numbers make no sense. And we went for the hunt for the truth. Right. So Ambika made stuck in the MOS pit. Critical analysis of MOS test methodology in TTS evaluation, which we've submitted to SSW, which is a double-blind conference, so don't tell anyone. So Ambika surveyed 133 papers at past Interspeech and SSW conference. SSW is Speech Synthesis Workshop Conference, just saying. And what were those papers measuring? Nobody knows. Some were reporting naturalness, some reporting quality, some were unknown, unclear, the multiple others. So we saw that there is like a lack of a standardization, like what we should measure at this time. Quality would have made more sense when it was more statistical parametric speech synthesis. But now, since these deep learning models are very nice, I think people going towards naturalness I feel personally, is a good step. But what were the labels on the scale? This is where the fun begins. They don't tell it. So 69%, which is 92 papers of 133 papers, did not tell like what were there on the scales. Could be one of the reasons why I never could reproduce those results, or we rather could never reproduce those results. And the general ITU standard is followed by 13.5% people, which is bad, poor, fair, good, excellent. And also there are some honorable mentions where someone says very annoying, annoying, slightly annoying, perceptible but not annoying, and almost real, which is a very weird scale to have. But yeah, there's an honorable mention. When Ambika told me about this, I was like, everyone should know about this. So result and conclusion, it's not me, it's them. In our experiments, different settings yielded different results. Suggested some recommendations and asked the paper conferences to provide a little bit more section to have more information. But Ambika can tell you more about this because she's amazing. And it was very hot. I was very happy with the results, like oof, all sweating but happy. Then one day, again, Gustav comes and says, one does not simply stop at speech synthesis. But, and I was like, panic. Okay. Right. And then I said that, so should we try OverFlow for speech and gesture synthesis? That we also make it generate motion. Who knows, maybe it works, maybe it doesn't. Spoiler, it did not. So I needed help. That was me. We missed one deadline and I needed help. So I joined forces with Power Rangers. Yes. So we tried VAs. It was it was very weird.
Me, that makes me feel like you don't want to get after. I don't think you don't want to get.
People tell me once you're old and you sleep weird on the bed, this is how you turn out. So this was quite human-like. This was very promising. Yeah.
You feel like you just don't want to be an actor. I don't think you don't want to get into the nitty-gritty.
The data set had no ninjas in it, but it still made this ninja type motion. So I think it was not working. Nothing worked. It was spicy, but not tasty. That's too much. Overdone. So then again, Gustav bestowed me his wisdom. Non-autoregressive diffusion model you should use. Yes. So long story short, this was me. I moved from OverFlow to non-autoregressive diffusion model like grad TTS. So we made this Diff-TTSG, Denoising probabilistic integrated speech and gesture synthesis. It was the first diffusion model that jointly learns to synthesize speech and gestures together. It's probabilistic in nature and not autoregressive, so it was relatively faster to train per iteration, and you could sample at faster speed than from OverFlow. And then it could be trained on small data sets from scratch because it also had this monotonic enforcement of the alignments, which is apparently a quite important thing to have when you're training a text-to-speech system with different sampling rates. Like from text to melody representation, where you have to upsample each discrete token multiple times. So it was very hot because the diffusion models everyone's talking about this from Stable Diffusion. Yes.
I have a small question. Why is it called TTSG?
Makes text to speech and gesture. It's a secret code. It's double blind. Don't tell anyone this. So it had the text encoder and a duration predictor, which we took from KTH people. And they use the similar process. We use a similar process from them, where we use this mu mail generated and start a diffusion denoising process from there. It's not exactly diffusion, DDIM or DDPM setting. It's a DPM setting where we can form this, I don't know how do I say, like this chain as an ODE and can sample from it iteratively. And then we use this mu mel and created like a conformer prenet, which will take this mu mel as an input and output what we call as mu motion, sort of. And then start the diffusion process for the motion from that. And so essentially, this the left half of this becomes a speech to motion synthesis pipeline, while the right half is text to speech pipeline. So we sort of fuse them both in a diffusion setting, and yeah, it worked. I will show you some samples. And remember, both motion and speech are synthesized from text only. So this was the input to the model, and this was the output.
And the train stopped, the door opened, I got out first, then Jack K got out, Roman got out, Louise got out.
Some more.
Dropped the car off in Miami, and that was fine. So we had a big plan, and so literally one morning, one by one, we would literally run down the stairs with our bags, and then we just ran.
And one more.
Jim asked if we should do a group home. It was a strange request, but then he insisted again. This time I had to shout, "No, please not again. No, never. I don't want to home. Please leave me alone." And I went out.
But be careful. AI can lie. I would never say no to Jim's hug. He loves it. See? See? Oh, that's not really a hugging photo, but lol. But how to evaluate such systems? This is also a challenge, like how do we know speech is good or not? So we sort of proposed or took inspiration from multiple sources and proposed like one unified sort of, well, not one, three step evaluation, where one, we first we evaluated the speech synthesized only with speech. The participant were not shown any other modality. So yeah, subjective MOS for audio only. Then we did the gesture only evaluation, where we used subjective MOS for motion video only. The audio was chopped off from there, and all they could see was this, and then rate if a human would make this type of motion or not. And by the way, when I say MOS, we did provide all the details into the paper. So yeah, we were not, they can't reproduce our baseline if we don't tell them our settings. So they can in our case. We also did appropriateness evaluation, where we showed the participants like matched and like in a random pair, of course. Like one side we had matched audio and motion, and the other side they had mismatched audio and motion. And where the higher rating basically means that it was easier for participant to select the one which had the matched motion and speech, which is actually a nice, if it works, it's like you should be able to select that this is jointly synthesized, sort of. Right. One of the last slides that I have is about my courses and teaching. I take this photo from the last year. It's so cool. I could not take it. I finished mostly all credits. I have more than 60 credits already, but because of some WASP mandatory courses, I'm still taking courses. I TA'd or TAing multiple courses. There's speech and speaker recognition, which I TA every year. Foundation machine learning, which Raymond TA'd, but I sort of helped to make assignments in the first or second iteration. And language engineering, which Johan is taking assignment of students right now, and I had to do all morning today. And I'm supervising 2.5 master student. The half is not a kid, it's just I shared it with Harm. So so future plans. I will plan to learn a little bit more about gesture synthesis. It looks very similar to text-to-speech problem, mainly because of like it has some own challenges of its own, but it's a continuous data, which I have been working with before, and I feel like maybe I might take part in maybe Genia challenge. It's a little uncertain because the deadline to TTSG was literally 1.5 weeks ago. So I'm not someone with a lot of plans. So this part is like, I've figured it out, but probably genius challenge or learn a little bit more about gesture synthesis. I will try to use advances in diffusion from the, like, if you go out there, there's so much things that have happened in diffusion, from control net to like better training or other ways of actually diffusing on the motion, on the data. So probably try something with that, play around. And like always, I'm open for collaborations. Let's get to work. You know. This slide was for Joe, okay, because he loves cat, but he's not here. So. But yeah, first of all, thank you everyone. You guys rock. I cannot thank my supervisors enough. Gustav, Jonas, Yoke, Eva, Simon, Gabriel, Johan, who have helped me and guided me at every time I was lost. And boy, that was quite a lot of time. And I would like to thank all of my collaborators and my friends for making me feel at home here and helping me whenever I get stuck. And again, that was a lot. And special thanks to Karina for listening the birch canoe slid on the smooth planks, non-stop and repeatedly with different weird models and sounds. Yes, for a million, bazillion, gazillion times. Yeah. If someone wants to know how to be patient, talk to Karina. And yes, thank you for my parents for attending this, my family and my friends for talking to me every day and making sure I'm still sane and doing good despite the distance. I really miss them a lot. And thank you all for attending the seminar and being part of this PhD journey with me. And RIP 509 fridge. Gone from 509, but always in our heart and perhaps basement. Yeah. Cool. That's all I had. I will stop the recording, yes, I know. Yeah.